Logical reasoning and biconditional statements. So first we're going to talk about some laws of reasoning, and the first one is the law of detachment. When you see the words, it sounds really complicated, but it's actually a very simple idea. It says that if P implies Q, remember the arrow means implies, if that's a true statement and P is true, then Q is true. So that doesn't mean that much, but what they're really saying is that you must have the hypothesis to state the conclusion. If you have a true statement, you need the hypothesis to state the conclusion. So remember, the hypothesis is the P. So remember, you can state that in if-then form, if P, comma, then Q, where P is the hypothesis and Q is the conclusion. So we need the hypothesis to state the conclusion. So when you're looking at these examples below, you have to be given the hypothesis to state the conclusion. So first one, we know the given is what we know to be true. If two segments are congruent, then they have the same length. So we are given also that we have two congruent segments. Now notice this is my P and it implies my Q, and what they've given me is my P. So therefore I could, since they give me the hypothesis, I can state the conclusion. I can state the Q, which is two segments have the same length. Remember, when we write down segments without bars, we're talking about a length, and lengths are equal, so those two are equivalent statements. So this one's valid because they gave us a P implies Q, and they gave us the hypothesis, so we can state the conclusion. Next example. If you're tardy 3 times, you must go to detention. So this is my P, and that implies my Q. Shay is in detention, so what they've given me is a Q. That doesn't work. We have to have the P, the hypothesis, and they haven't given to us. This is invalid. Next example. If a student passes his classes, then the student is eligible to play sports. So there's my P, and that implies my Q. Ramon passes his classes. That's a P, because he passed his classes. So they've given me the hypothesis, however I can state the conclusion. Conclusion is Ramon can play sports. This is valid. The next bit of logical reasoning we're going to discuss is the law of syllogism. It states that if P implies Q and Q implies R, if those are true statements, then I can conclude that P implies R. If P implies Q, notice the connection there, Q implies R, then I can say that P implies R. So this is a demonstration of how one thing logically leads to another. We think this way all the time, that one thing follows another. Let's look at some examples below. The law of syllogism. For this first example, we're given that if the measure of A is less than 90, then angle A is acute. If angle A is acute, then it is not a right angle. So follow the reasoning. P implies Q. Okay, notice how angle A is acute is Q, and here it is again. Q implies R. Then I can make the leap. I can say that P implies R. If the measure of A is less than 90, then it is not a right angle, which is exactly what the conjecture is. So this one is valid. Next example. If we're given that if a number is divisible by 6, then it is divisible by 2. If a number is even, then it is divisible by 2. Conjecture, if a number is divisible by 6, then it is even. Now, the thing you might get caught up in is that might even be a true statement, but is this valid by the law of syllogism? Does it follow the rules of the law of syllogism? That's the question. So if I consider this my P, if a number is divisible by 6, then it is divisible by 2. There's my Q. And then I have a problem. I have something different that hasn't been talked about. So that'd be like an R. And then there's divisible by 2 after that. There's my Q. So we've got a problem here. And one is that we don't have the one thing follows another. It doesn't follow the law of syllogism. Now, one thing you got to watch out for, sometimes you can flip the sentences around and make it work. Then maybe they gave it to you in the wrong order. So, for example, if I called this my P, if a number is even, then it is divisible by 2, that's my Q. Well, then I'm still not going to work because, this would be a new thing. A number is divisible by 6, which is completely unrelated to the other two. There's my R. And then it is divisible by 2, which back to my Q again. And things don't work. So do check the order and see if it works. This one is invalid. Given, if an animal is a mammal, then it has hair. If an animal is a cat, then it is a mammal. Okay, notice the mammal here that they have in common. In fact, this one, looking at it, I believe it is backwards, because if we said this was P, the animal is a mammal, and then it has hair, then that doesn't work because I should have hair again. I should have a Q there. And that's not what's going on. So what I need to do is change the order of my sentences to make this one work. So if I said, if an animal is a cat, P, then it is a mammal, there's my Q. If an animal is a mammal, there's my Q again. Then it has hair, there's my R. Then I can conclude that P implies R. So that'd be these two. If P implies Q and Q implies R, then P implies R. If an animal is a cat, then it has hair, which is exactly what they concluded. This is valid. Last example. If you leave your car lights on at night, then your battery will drain. If your battery is drained, then your car might not start. If you leave your car lights on at night, I forgot the on there, there's my P, then your battery will drain, there's my Q. If your car battery is drained, there's my Q. It implies it might not start, there's my R. So my conclusion should be that P implies R. If you leave your car lights on at night, then your car might not start. So Samantha left her car lights on at night. What might happen? Her car might not start. The last thing we're going to talk about is biconditional statements. And I believe I mentioned this briefly in another video. But a biconditional statement is when we use if and only if between our two parts, our P and our Q. So we don't use if then. It doesn't begin with if. In the middle, we should see if and only if. An example, a polygon is a triangle if and only if it has 3 sides. So when we write this down, we use a double arrow showing that the implication goes both directions. So if I get a biconditional that's true, then all 4 of the statement forms are true. Saying P if and only if Q is really saying all 4 statement forms are true. So the original, P implies Q, the converse, Q implies P, the inverse, not P, implies not Q, and the contrapositive, where you flip them and negate them, not Q implies not P. So if the biconditional is true, all 4 of them are true. A true biconditional is a double implication, and the original statements and the converses are true, which makes all four statement forms true. If you've forgotten, remember the original statement is logically equivalent to the contrapositive, and the converse is logically equivalent to the inverse. You have to know that. Logically equivalent means they have the same truth value. If one's true, the other's true. If one's false, the other false. So the original and the contrapositive are both the same. The inverse and the converse are both the same. And if a biconditional is true, they're all true. Here comes the crucial point. To see if a biconditional statement is true, you have to check the original statement, which automatically checks the contrapositive because they're the same, remember? And you have to check the converse, which automatically checks the inverse. Here's an example below. A figure is a square if and only if it has 4 sides and 4 right angles. Now the problem here is when you read that with if and only if, it can seem so logical until you look at it both ways. You have to look at the original and the converse. So the original, we'll put it in if-then form. If a figure is a square, then it has 4 sides and 4 right angles. That's a true statement. Now, because the original is true, we know the contrapositive is true. Okay, we have to check the converse too. The converse, we flip the P and the Q. If a figure has 4 sides and 4 right angles, then it is a square. Now this is false because there's another figure that has 4 sides and 4 right angles. In other words, there exists a counterexample. It could be a rectangle. A rectangle has 4 sides and 4 right angles. So that is not a true statement because there exists a counterexample. Remember, even if it's true most of the time, if you have one counterexample, it's automatically false. Now, since this statement is false, the converse, we automatically know the inverse is false. So since the converse was false, this biconditional is false. We have to have the inverse and converse true, which makes them all 4 true for a biconditional to be true. Reminder here, every single definition that exists will all create true biconditionals. So all 4 statement forms are true for definitions.